Hello there, and welcome to Sleepy Cosmic Podcast, where we wander beneath velvet skies, following ancient light on its unhurried path through time. Tonight, as we settle under quiet constellations, a hush spreads through the crust of our world. Beneath the surface, below your feet, under the oceans, and inside the mountains, something stirs. Not violently, not suddenly, but slowly, like the shift of breath in a sleeping body. Earthquakes are multiplying, yes, but not in a way that alarms. Instead, they appear in clusters and whispers, in places long thought quiet. And as we begin to trace their patterns, we find ourselves drawn not just inward, but outward, toward the sky, toward the drifting presence of something unusual, the interstellar traveller known as 3-Eye Atlas. If this kind of quiet wonder helps you rest, I'd be grateful if you tap like or subscribe. No pressure at all. And if you're joining us from somewhere special tonight, maybe you'd like to whisper your location and local time in the comments. It's always comforting to know we're not alone under these stars. Now, dim the lights, maybe turn on a fan for a soft background hum, and let's ease into tonight's journey together. We begin in the deepest parts of the ocean, where darkness folds like velvet and pressure presses with ancient weight. There the Pacific plate drifts with steady persistence, pressing against its neighbours in the long, slow dance of tectonic time. Normally these movements are quiet, imperceptible to us, but lately more and more tremors are being recorded along subduction zones, deep beneath ocean trenches where one plate slides beneath another like a sigh. Some of these quakes are too small to feel, others ripple just enough to be noticed briefly by those who live near the sea. What's curious isn't their size, but their timing. A cluster here, then silence, a sudden swarm there, followed by stillness. This rhythm feels different, as though the planet is murmuring in its sleep. At the same time, solar observatories have begun recording a subtle increase in flux from the sun, variations in solar wind and tiny pulses of energetic particles streaming toward us. These aren't rare in themselves. The sun is a living star, always shifting, always breathing. But when compared with the recent rise in seismic activity on Earth, the alignment becomes worth noticing. Earthquakes, after all, are the outward expression of internal tension, and tension builds when the planet is pulled. The moon's gravity does this constantly, lifting tides and subtly shifting the crust. But the sun too exerts its own quiet pull. Its gravity tugs at Earth's molten core just enough to add a beat to the planet's rhythm. When an object like 3-Eye Atlas enters the equation, a body from beyond our solar system, travelling at interstellar velocity, it adds a layer of uncertainty. Though tiny compared to a planet or even a moon, its passage through the heliosphere may carry a gravitational or magnetic presence we don't yet fully understand. Could it be that something in its wake is altering the flow of solar wind? Or perhaps nudging the sun's rhythm, just enough to change the way it tugs at Earth? Astrophysicists still debate whether such interstellar bodies have any tangible effect on solar or planetary dynamics. The math is elusive, the distance is enormous, and the energy is small. But it's not the certainty we're after tonight. It's the possibility, the quiet wonder of noticing the pattern, the thrill of imagining what might connect these faraway pulses to the restless heart of our world. Beneath the ocean floor, sensors pick up low-frequency rumbles, like the deep notes of a planetary cello. Some are normal, some are new. Some emerge from places where faults were once believed dormant, faults now awakening from geological sleep. In Alaska, in the South Pacific, in the long trenches off the coasts of Chile and Japan, clusters of microquakes have been recorded, faint and precise. Often, they precede no major shift. Sometimes, though, they are the prelude to something more. Scientists call them foreshocks. Nature calls them murmurs. To listen for these movements, researchers use instruments like seismometers, buried miles deep, hydrophones resting on the ocean floor, and satellites measuring the slightest shifts in Earth's crust. All of them, tuned like instruments, listening for the planet's quiet music. And perhaps, somewhere in that music, there is a harmony being formed with what's happening in space, a gravitational duet, a magnetic refrain. Maybe 3i Atlas is not just a visitor but a messenger, reminding us of how all things drift and touch, of how Earth too is part of a larger song. In our quiet observatories watching both sea and sky, the instruments whisper back their data, not screaming, not warning, just whispering, the way ancient light always does. So we begin here, with silent tremors under still oceans and a new rhythm slowly emerging. A rhythm we'll follow, unhurried, as it leads us across the stars and back again. Beneath the surface of our world, where molten currents drift slowly through Earth's mantle, something ancient stirs in response to light from above. Not the visible kind, not the golden warmth that greets our mornings, but a slower, deeper influence. Sunlight, yes, but refracted through time and gravity. The sun exerts a quiet authority over this planet, not only through heat and light, but through the gentle pull of its mass across vast space. And it is this subtle gravity that we now feel pressing ever so faintly on the restless heart of our world. The molten core of the Earth, composed primarily of iron and nickel, spins in layered motion, solid at the centre, liquid surrounding it, dynamic and alive. This movement generates our magnetic field, and that magnetic field shields us from solar wind. But the relationship isn't one-directional. The solar wind too touches us. It kisses the top of our atmosphere with charged particles, disturbs our magnetic field, and in doing so it may ripple down into places we cannot see. At the core mantle boundary, over 3,000 kilometers below the surface, currents of molten metal swirl with unimaginable pressure. The sun's gravity, though distant, adds a persistent tidal force to this motion. This force isn't dramatic, it doesn't cause immediate shocks or shudders, but like the moon raises tides in our oceans, the sun lifts tides in Earth's very rock. These are solid tides, and they are real. Over the course of a day, Earth's crust subtly bulges and relaxes, responding to the gravity of the sun and moon alike. When the solar tide and lunar tide coincide, their effects amplify slightly. And lately, these tidal harmonies seem to be resonating with something deeper. Earthquakes have increased not only in number, but in curious timing, appearing more often during certain solar alignments, at moments when gravitational tugs from both the moon and the sun align just so. And now, another presence enters this invisible conversation. 3i Atlas. A body from outside our system, beyond the gravitational norms we are used to. It doesn't need to be large to matter. Its mere approach, slicing through the heliosphere like a whisper through a curtain, may be shifting the sun's behaviour in ways we don't yet understand. We know that comets and interstellar objects sometimes cause perturbations, not by direct contact but by influencing plasma, by stirring particles in the solar wind, or by warping magnetic fields in localized arcs. These effects are small but not zero. In sensitive systems like the ones deep inside Earth, they may resonate. We can imagine this as a tuning fork. The sun vibrates with its own frequencies, pulsing with cycles of activity. Earth listens, always, through its molten interior and tectonic skin. And when something causes the sun to shift, perhaps a gravitational nudge or a change in magnetic current, that subtle change may echo through the system. Earth may answer. Astrophysicists still debate whether external objects like 3i Atlas can influence solar cycles. There is no clear consensus. Some argue the math doesn't support any significant change. Others suggest that in complex systems, even small perturbations can cascade into larger consequences, especially when resonance is involved. our own observations are limited by time. We've only watched the sun closely for a few centuries. Instruments like SOHO, SDO, and Parker Solar Probe give us glimpses of the sun's outer behaviour, but the inner life of our star remains mysterious. It breathes, but we don't fully know how. Still, there are patterns we cannot ignore. Solar activity, like flares and coronal mass ejections, has recently shown signs of unusual timing. Some events are arriving earlier in the cycle than expected, others appear oddly clustered, and while correlation is not causation, the quiet rise in Earth's seismic activity seems to hum in time with these solar shifts. The Pacific Northwest, for instance, has seen a modest but steady increase in deep, low-frequency tremors, not destructive quakes, but slow slips, silent earthquakes that last for hours or even days. These events release energy gradually, too slowly to be felt, but enough to shift tectonic plates by millimeters. They were once rare. Now they seem to follow a rhythm, one that some researchers think may link to fluctuations in solar energy and geomagnetic storms. Further south, in regions like Central America and the Philippines, fault lines have also grown more active. Swarms of small quakes rise and fall in waves as though waiting for a cue. Could the sun's shifting influence, stirred perhaps by 3i Atlas, be that cue? It is not the kind of question science can answer in haste. We must watch, we must listen, we must compare data across years, across solar cycles, and across the wandering paths of objects from beyond. But for now, we can lie back and simply imagine the sun quietly responding to a new visitor, Earth listening in its deep interior, and us, here on the surface, feeling the tiniest pulse beneath our feet. This is how it begins, not with disaster, not with fear, but with awareness, a change in the rhythm, a soft breath beneath the surface, a feeling that perhaps, just perhaps, the core is listening, and so are we. Far beyond the familiar pull of our solar system, past the known orbits of the outer planets and the whispering haze of the Kuiper Belt, something unusual entered our skies. Not long ago, but long enough to stir our curiosity. Its name is 3i Atlas, and it belongs to a very rare class of visitor, an interstellar object. That is, it comes from outside, from the space between stars, from the quiet dark that spans the light years. It is the third such object ever confirmed. The first, Oumuamua, slipped past us with a mystery all its own. Its shape, its motion, and its silence all left us with more questions than answers. The second, Borisov, was more clearly a comet, trailing a soft tail of gas and dust as it moved along a graceful arc. But 3 Atlas, the third, has arrived at a curious moment, when both solar activity and Earth's inner rhythm are shifting in tandem. Its trajectory is not chaotic. It moves with quiet certainty, like a ship passing through unfamiliar waters, unaffected by the expectations of our solar system. And as it crosses into the influence of the sun, our instruments pick up changes, not necessarily because of its mass, which is small, but because of its interaction with magnetic fields, particle flows, and possibly gravitational harmonics. 3i Atlas is not aiming at Earth. It passes instead through the outer solar system in a gentle arc, but its presence adds a new complexity to the quiet patterns we've known. The heliosphere, the vast magnetic bubble that surrounds our solar system, is sensitive. It's shaped by the solar wind, by galactic particles, and possibly by visitors like this. The solar wind itself is not a constant stream. It breathes, it pulses, it carries energetic particles outward in spiraling waves, driven by the sun's magnetic field. These spirals, known as Parker spirals, can carry disruptions far into space. When an interstellar object moves through this environment, it may cause a minor stir, like a finger grazing the surface of a calm pond. Some researchers suspect that 3i Atlas, despite its size, might have intersected with these spirals in a way that triggered new solar behaviour. Perhaps it disturbed a region of magnetic tension. Perhaps it changed the charge balance in a local solar wind stream. Or perhaps it simply passed through unnoticed, leaving only questions in its wake. Even if its influence is only symbolic, there's something deeply human about watching the sky and linking it to what happens beneath our feet. We've always done this. In ancient times, comets were seen as omens, eclipses were feared and revered. Earthquakes, when they came, were blamed on celestial imbalances. Today, our tools are sharper, our understanding is clearer, but the instinct to connect sky and ground still lives in us. We know now that some of these connections are real. Solar storms, for example, can cause geomagnetic disturbances on Earth. These disturbances affect everything from satellites to electrical grids. In rare cases, they have even been tied to disruptions in animal migration and shifts in atmospheric pressure. The link between the Sun and Earth is not just poetic, it is physical. Could an interstellar object, small, distant and fast, play a part in that link? It's uncertain, but the possibility is not dismissed. As more of these objects are detected, and as our instruments become more sensitive to the invisible flows of energy and magnetism, we may find that visitors like 3i Atlas leave soft fingerprints on the systems they pass. Even now, astronomers track its course through the solar system, mapping its origin, its speed, its chemical makeup. Some theories suggest it came from a dying star system. Others think it was ejected during the violent formation of planets in a distant system. Flung out into interstellar night, it has wandered ever since. Its path brought it here, where it now coexists briefly with us, sharing the light of our sun, brushing through its field, bending slightly under its gravity. For a time, 3i Atlas becomes part of our system's choreography. And perhaps, just perhaps, the Sun feels this shift too. It's possible the solar surface, already chaotic and responsive, reacts to this presence in small ways. Solar filaments may stretch, magnetic loops may twist a little tighter, bursts of plasma may release with subtly different timing. These events may, in turn, affect the rhythm of solar wind, and when that wind reaches Earth, it brushes against our magnetosphere and faintly our crust. Seismic observatories, mostly silent except during major quakes, have been busy. Their data shows an uptick not only in large quakes but in small ones. Background noise, the ever-present low rumble of Earth's internal motion, has grown slightly more textured. Perhaps that's coincidence, perhaps it's seasonal. But some researchers are watching this correlation closely, not as a conclusion, but as a question. What happens when a stranger enters the Sun's domain? What wakes when a new gravity crosses familiar paths? Tonight, we rest in the gentle mystery of it. We trace the journey of 3i Atlas, not to predict, but to wonder, to consider how even the smallest presence from the stars may ripple quietly through the systems we thought we knew. High above our heads, wrapped invisibly around Earth like a silent shell, lives the magnetosphere. It hums with quiet strength, shielding our planet from solar wind and cosmic radiation, bending streams of charged particles so they dance away rather than dive inward. Without it, life on Earth would be exposed to radiation fierce enough to slowly strip the atmosphere itself. But this magnetic cloak, though powerful, is not unchanging. It flexes, it breathes, and at times, it falters, especially when the sun begins to stir. The magnetosphere is born from deep within Earth's molten core. As liquid iron swirls and rotates, it generates a magnetic field that extends far beyond the surface, thousands of kilometers outward, touching the edge of space. It forms a teardrop shape, stretched by the solar wind, pushed and sculpted by the flow of charged particles coming from the sun. On the sunlit side, it compresses. On the night side, it trails out into a long magnetic tail. Within this structure, delicate layers interact. regions of trapped radiation, boundaries where solar and planetary fields meet. When the sun is calm, the magnetosphere holds steady. But when solar storms erupt, when flares or coronal mass ejections burst into the solar wind, they bring surges of energy that crash against the magnetosphere's edge. The field ripples, the tail stretches and flutters. Sometimes charged particles breach the shield and flow into Earth's upper atmosphere, creating auroras. And sometimes these interactions do more than paint the skies. Some scientists believe that strong geomagnetic storms can influence tectonic stresses, particularly in areas already near a tipping point. The connection isn't fully understood, and the evidence is sparse. But there are subtle hints, instances where large earthquakes have followed soon after major solar events. One such episode occurred in March 2015, when a powerful solar storm struck Earth. Days later, a significant earthquake shook Chile. Though the timing may be coincidence, it added to a growing curiosity among geophysicists and space weather researchers. Could geomagnetic fluctuations in some cases act as a trigger? Astrophysicists still debate whether these forces are truly linked. Some argue the energy from solar storms is far too weak to affect tectonic plates directly. Others point to the delicate balance of stresses within Earth's crust, and suggest that even a small nudge, perhaps electromagnetic in nature, could hasten a release of built-up strain. The magnetosphere is not a rigid shell after all. It behaves more like a membrane, responding to solar rhythm with grace and tension. As 3I Atlas draws nearer to the Sun, its presence may contribute to subtle shifts in the solar wind. Even slight changes in particle flow or magnetic alignment could alter the shape of our planet's protective shield. Satellites like Themis and Cluster monitor these dynamics constantly. They have recorded instances where magnetic reconnection, a kind of snapping and reforming of field lines, sends bursts of energy cascading toward Earth's poles. These moments, though fleeting, change the energy balance in the upper atmosphere, which in turn may affect pressure systems, jet streams, and even ionospheric conductivity. Down below, in the crust of the Earth, sensitive instruments sometimes pick up unexplained anomalies, tiny shifts in conductivity, sudden pulses in ultra-low frequency electromagnetic waves. These signals come and go, often with no clear pattern, but occasionally lining up with solar activity or geomagnetic fluctuations. In places like Japan, where tectonic monitoring is especially precise, researchers have noticed that electromagnetic precursors sometimes appear before earthquakes, not always, not predictably, but often enough to keep the question alive. Are we seeing echoes of space weather beneath the ground? If so, 3I Atlas may play a quiet role. As it disturbs the solar wind, perhaps minutely, those changes ripple outward. The Sun responds in turn, sending subtle fluctuations into space, which Earth receives. The magnetosphere, like a tuning surface, reacts. And somewhere in that reaction, pressure shifts just enough along a fault line, triggering a quake that was already nearly ready to occur. Again, this is speculation, not established science. But it is the kind of wondering that leads to new observations, new instruments, and new ways of listening to Earth as part of a cosmic system. Even now, our magnetosphere is changing. Its north and south poles wander slowly over time, and the field itself is weakening by small amounts each decade. These shifts are normal, part of Earth's long magnetic cycle, but they also suggest that our shield is dynamic, responsive, sensitive, and intimately tied to what happens in space. As we drift through this moment in deep time, 3I Atlas remains a distant traveller, but its presence reminds us that Earth's systems are never truly alone. From molten core to magnetic shell, from quiet crust to flaring sun, every layer of our world is in motion, influenced by rhythms we're only beginning to understand. So we rest beneath this shield, beneath this invisible guardian that shields us while remaining nearly undetectable, And we wonder, not in fear but in curiosity, how the breath of stars, the drift of interstellar guests, and the slow pull of solar light might all leave fingerprints on the silent patterns beneath our feet. The sun, for all its warmth and constancy, is not a fixed presence. It pulses, it flickers, it shifts in ways that feel slow to us, but are anything but static. Its surface, a roiling ocean of plasma, is shaped by magnetic fields that twist, reconnect, and sometimes snap, releasing immense energy in flashes we call solar flares. Over longer cycles, the sun enters periods of higher and lower activity, like a cosmic breath expanding and contracting across decades. This solar rhythm is known as the solar cycle, and it follows an approximate pattern of 11 years, rising from quiet to active and then back again. During its active phase, sunspots darken the surface like freckles, magnetic storms ripple outward, and the solar wind intensifies. At its quietest, the surface smooths and the winds hush. Yet even during these minimum years, the sun is never truly still. At present, we find ourselves entering an unexpectedly lively phase. Solar Cycle 25, officially underway since late 2019, was forecasted to be modest, but it's showing signs of growing more intense than scientists initially predicted. More sunspots, more flares, more bursts of energy streaming toward our world. And just as this cycle heats up, 3I Atlas arrives in our cosmic neighbourhood. Two crescendos rising together, two unknowns intersecting in deep time. Some researchers have begun quietly asking whether the interstellar object's presence, though subtle, could be influencing this uptick in solar mood. Could the gravitational wake of a fast-moving visitor tug at the solar surface in some gentle way? Or might it be disturbing magnetic equilibrium through charged particle interactions as it passes through the heliosphere? We don't yet have a firm answer, but we do know that the Sun is a sensitive system. Its outer layers, especially the corona, respond to changes in the solar magnetic field with dramatic outbursts. These events, in turn, ripple outward through the solar wind, altering the magnetic environment of the entire solar system, including Earth's. When these energetic pulses strike Earth's magnetosphere, they can trigger geomagnetic storms. And while the auroras that follow are beautiful, other effects are more hidden. Some scientists suspect these storms may cause minor shifts in atmospheric pressure, potentially influencing weather patterns. Others wonder whether the electrical currents they induce in Earth's crust could, under the right circumstances, coax a fault line toward release. It's not a settled matter. Astrophysicists still debate whether any causal link exists between solar flares and seismic activity. Most large earthquakes occur independently of space weather, but curious patterns remain. Certain regions appear more seismically active during peak solar cycles. Some large quakes have coincided with geomagnetic disturbances. Whether this is coincidence or correlation remains open to interpretation. One fascinating detail lies in the timing of seismic events relative to solar flare arrival. When a powerful flare erupts, it takes light just over 8 minutes to reach Earth, but the charged particles arrive hours or even days later. If a link exists, it may not be immediate. The Earth's systems may need time to absorb and respond to the change. In Japan and California, both regions known for meticulous earthquake monitoring, researchers have quietly compiled decades of data. Some have noticed an increased clustering of seismic swarms following major solar flares. Again, the evidence is tentative, but it invites deeper listening. To track the solar heartbeat, we rely on a range of observatories. The Solar Dynamics Observatory, SDO, watches for flares and coronal mass ejections. The Parker Solar Probe dives closer to the Sun than any craft before it, flying through the corona to taste the origin of solar wind. Together, these instruments give us glimpses into the Sun's shifting mood, and right now, the data shows a rise. More frequent flares, more energetic events, and more turbulence in the solar wind. Whether this activity is part of a natural variation or subtly linked to through-eye atlas, we don't yet know. But the timing is poetic at least. One system waking just as another passes near. Down here, on Earth, we notice in our own quiet ways an increase in auroral displays, a few extra tremors near the edge of fault zones, a shimmering in the sky that wasn't there before. None of it proves anything, but together it whispers a question into the silence. What else stirs when the sun begins to sing? It's easy to forget that our planet floats within a sea of space weather, not just emptiness, but a changing environment of magnetic waves and charged particles, shaped by the mood of our nearest star. When that mood shifts, Earth feels it, sometimes with beauty, sometimes, perhaps, with motion beneath the surface. And so we watch the solar cycle as we might watch a tide, knowing that it rises and falls with a rhythm older than humanity, a rhythm now complicated perhaps by the quiet passage of the three-eye atlas. In this deep night we imagine the sun glowing quietly behind the veil of atmosphere. It pulses with invisible light, hums with magnetic tension, and sends its wind across the solar system like a breath. And as Earth listens, something stirs in the crust, in the mantle, in the molten places where time forgets to hurry. Beneath our feet the world is never truly still. Even in the calmest landscapes under soft meadows, quiet plains, or the settled seabed, there is motion. It may be slow, like the drifting of continents, or sudden, like the jolt of a fault releasing its burden. Lately, across multiple regions, a new pattern has emerged. Seismic clusters, earthquake swarms, not necessarily destructive, but frequent. Like whispers in the crust, speaking in rhythms we're just beginning to hear. In California's Imperial Valley, for example, a swarm of small quakes rose and fell over a few days, not causing damage, but enough to draw attention from those who watch the Earth closely. In Iceland, near the Reykjanes Peninsula, dormant volcanic systems have stirred again, with tremors becoming daily companions. Along the Pacific Ring of Fire, minor seismic events have begun appearing like dots on a growing constellation. No single quake is alarming on its own. But the pattern suggests a deeper question. Why now? Some geophysicists are exploring whether these clustered tremors might be influenced by shifts in the broader environment, particularly the space environment. It's not a mainstream idea yet, but it's being studied with increasing care. The concept is simple, though the mechanics are not. Could solar energy and geomagnetic shifts, perhaps disturbed by something like three-eye atlas, be playing a subtle role in triggering these events? One proposed mechanism is the piezoelectric effect. Certain rocks, like quartz-rich granite, can generate electric charges when stressed. If solar or geomagnetic activity changes the electrical balance in the Earth's crust, it could influence how these rocks behave, perhaps nudging a fault line already near the edge. Another idea involves telluric currents, natural electrical currents that flow underground, influenced by solar storms and geomagnetic fluctuations. These currents have been observed to vary during space weather events. Some researchers have proposed that their fluctuation might correspond with shifts in subsurface pressure, especially in fault zones already poised for motion. Astrophysicists still debate whether these interactions are strong enough to matter. Earth's crust is massive. Its inertia is enormous. But the key lies not in brute force, but in timing. A system already stressed to the brink may not require much to yield. A whisper, not a shout. A gentle nudge, not a push. And what of three-eye atlas? It remains far from Earth, yet its presence in the solar system adds complexity to an already sensitive network. As it moves through regions shaped by the sun's magnetic field, it may alter plasma behavior in minor but noticeable ways. If that changes enough to shift the solar wind, even slightly, the effects could ripple outward, eventually brushing Earth's magnetic field, and from there, perhaps stirring something below. This isn't fantasy. We know from satellite data that geomagnetic storms can change atmospheric pressure. We know that sudden drops or rises in pressure can, in rare cases, correlate with seismic activity, especially in shallow fault zones. The Earth listens to the sky more than we once believed. In Alaska, recent tremors near the Denali Fault have prompted a review of past quakes and their timing. Curiously, a few larger events over the past 2 decades occurred within days of strong solar storms. Coincidence, perhaps? But the coincidences are adding up. Meanwhile, Japan's meticulous records show that in some regions, the rise of deep, non-volcanic tremor, tiny earthquakes occurring in the lower crust, often coincides with bursts of geomagnetic activity. These tremors don't break the surface, they don't damage buildings, but they offer a window into how energy moves through the Earth, how stress accumulates and releases without warning. We've begun to develop instruments specifically for this type of monitoring. Networks of magnetometers, seismometers, and atmospheric sensors work together now, listening for patterns. The data is vast, the signals are faint. But in time, they may help us understand whether cosmic rhythms truly resonate with Earth's crust. Perhaps the real question is not whether space affects Earth, but how much. The line between space weather and geophysical events is growing thinner, not thicker, as we learn more. And if that's true, then even the quiet passage of an interstellar object could become part of the conversation. Three-Eye Atlas might be only one note in a larger symphony, barely audible, easily missed. But if it causes the sun to shift slightly, and the sun's shift alters the wind, and the wind brushes our magnetic field just so, then somewhere deep below a plate might slip, a crack might lengthen, a whisper might turn into motion. Still, we must be careful. These ideas are not proof. They are questions, beautiful questions, the kind that science holds gently in its hands, waiting for clearer answers, waiting for more time. For now, we observe. We feel the quiet beneath our feet, and we remember that the Earth, like us, responds to things it cannot always see. The tremors may be small, the swarms may pass, but the rhythm they follow feels new, and that, in itself, is worth listening to. Long before we had instruments, long before satellites and seismic graphs and deep space observatories, we listened with our stories. Across centuries and cultures, people noticed patterns. They watched the sky and the land. They noticed that sometimes strange things in the heavens were followed by motion on Earth. Comets, eclipses, bright stars out of place. These were taken as omens. And when the ground shook, it felt like a conversation between worlds. Of course, we now understand that not every comet brings disaster, and not every quake comes from the sky. But the impulse to link celestial and terrestrial events was never foolish. In fact, it echoes a truth we're only now beginning to explore through science. Earth does not live in isolation. It is wrapped in layers of influence, solar, magnetic, gravitational, that stretch far beyond the atmosphere. And sometimes, just sometimes, those ancient instincts may have noticed something real. Historical records show a few strange alignments worth pondering. In the early 1850s, during a period of strong solar activity known as Solar Cycle 10, several large earthquakes occurred in South America and Asia, within days of powerful solar flares. In 1989, a geomagnetic storm caused by a solar coronal mass ejection knocked out power across Quebec, and days later, a rare seismic swarm was recorded in the Arctic. These events might be unrelated, but they remain curious. More recently, in 2004, one of the most powerful earthquakes ever recorded, the Sumatra-Andaman quake, occurred just after a significant burst of solar activity. Again, coincidence cannot be ruled out. But as patterns accumulate, some researchers are returning to these historical pairings with fresh eyes and better tools. What if, they ask, there really is a threshold effect? What if Earth's crust is like a taut rope? ready to snap with just a little added pressure. And what if solar events, altered even slightly by phenomena like 3i Atlas, provide that last faint tug? Astrophysicists still debate whether these correlations hold up statistically. Some believe the patterns are artifacts of selective memory. Others argue the evidence deserves more attention. A few pioneers in geophysics have begun building models to explore how solar-induced geomagnetic shifts could impact fault lines near critical stress levels. One theory involves the ionosphere, the thin shell of charged particles that surrounds Earth's upper atmosphere. During strong solar events, this layer becomes highly energized, increasing conductivity in the atmosphere. This, in turn, could influence the Earth's electric field and subtly change how stress behaves deep in the crust. Another idea centers on the coupling of the atmosphere and lithosphere. Under certain conditions, changes in atmospheric pressure, especially following geomagnetic storms, can send waves of pressure downward. These pressure waves might reach fault zones and interact with existing stress in unpredictable ways. But beyond the models and theories, there is something quietly poetic in the idea that ancient watchers may have sensed a connection before science could measure it. The silent watchers of old, shepherds, farmers, monks, stood beneath the same stars we do now. They felt the ground tremble and looked upward, wondering. For Atlas joins that lineage of celestial phenomena, a visitor from beyond drifting through the solar system not with drama, but with quiet persistence. Unlike comets that dazzle and disappear, it moves with little fanfare. But its presence is no less compelling. It reminds us that space is not still, that the heavens are not finished speaking. In some ways, our instruments are just the extension of those ancient eyes. We still look up, we still wonder, but now we listen with seismographs tuned to a whisper, with magnetometers that detect the breath of solar wind, with spacecraft that hover between stars and relay what they feel back to us in silent data. And still, the tremors come. In Italy's Apennine Mountains, swarms of microquakes have started to appear in regions once thought quiet. In Turkey, slow slip events have gently shifted entire fault zones over weeks, with no single quake to mark the motion. In Chile, the long spine of the Andes remains restless, responding to forces we can only partly trace. We no longer assume every quake has a celestial cause, but we no longer ignore the sky either. We are learning to hold both truths at once, that Earth is a system unto itself, and that it is also part of something much larger, a field of invisible currents, drifting gravity and ancient light. So tonight, as we settle into this moment of stillness, we drift back through memory, not just our own, but the planet's. We remember that those who came before us watched and listened too. They may have lacked our instruments, but they had time, generations of it, enough to notice patterns. Perhaps we're just beginning to catch up. 3i Atlas passes silently above, unseen by most, untouched by atmosphere, but its journey echoes through us in small ways, in questions asked, in sensors triggered, in old stories remembered. And maybe that's the greatest influence of all, not what it causes, but what it calls forth in us. The desire to listen closely, to connect sky and soil, to remember that even the faintest traveller can leave a trace, if only in the rhythm of our wandering. High in Earth's atmosphere, where the edge of space brushes the topmost layers of air, the auroras begin. These curtains of shifting light shimmer in greens and purples, dancing silently across the poles. We've watched them for centuries, called them by many names: northern lights, spirit fires, celestial veils. But behind their beauty lies a conversation between sun and earth, a quiet exchange of particles and fields, and possibly the faint echoes of something deeper. Auroras form when solar wind, a stream of charged particles from the sun, strikes Earth's magnetosphere. Most of the time, the magnetosphere deflects this wind. guiding it along field lines toward the poles. There the particles collide with atoms in the upper atmosphere, releasing light in graceful waves. We see them as beauty, but they are in fact signals, signs that the sun has sent something and that Earth is responding. During periods of increased solar activity, the auroras grow brighter and drift farther south. They appear in places where they are rarely seen, above forests in Canada, across skies in northern Europe, and even, on rare occasions, over the central United States or southern Australia. These brightening events often follow solar flares or coronal mass ejections, which surge through space and disturb the quiet balance of Earth's magnetic field. Recently, though, the auroras have begun appearing more frequently, and sometimes more quietly, not always tied to large solar flares, not always following the patterns we expect. There are reports of subtle auroras flickering at high latitudes without the usual storm signatures. Scientists studying these events have begun to wonder whether other influences, perhaps faint shifts in solar wind caused by unexpected changes in the heliosphere, are at play. 3I Atlas, as it travels through this environment, may be one such influence. Though too small to create its own magnetic field, it could still disturb local plasma streams, triggering minor realignments in the Parker spiral, the structure formed by the rotating outflow of the solar wind. These realignments could, in turn, lead to small but widespread variations in solar particle density, and when those particles reach Earth, even if weakly, the magnetosphere may flicker in response. That flicker doesn't always produce dramatic storms, but it may still create what are called subauroral ion drifts, subtle changes in the ionosphere that cause electric fields to move and spread across large regions. These fields, while invisible, can alter the behavior of satellites, GPS systems, and even the electrical properties of Earth's upper crust. Some geophysicists believe that under the right conditions these changes might cascade downward, affecting atmospheric pressure systems, altering ionospheric conductivity, and even impacting tectonic activity. The process isn't linear. It's not cause and effect in the way we usually think. It's more like resonance, a harmony between different layers of the Earth system, set in motion by something small and far away. And so we return to the auroras, not just as lights in the sky, but as messengers. They tell us that the magnetosphere is listening, that it is responding to a change. Whether that change is caused by solar wind, solar mood, or the presence of a traveller like 3I Atlas, we don't yet know for certain. But the timing is compelling. In early March of this year, a series of auroras appeared across Scandinavia and northern Canada, unexpectedly vibrant and not linked to any major solar flare. A day later, a small but unusual seismic event was recorded near the Arctic Circle. It was shallow, brief and harmless, but rare for the region. Days after that, a mild geomagnetic disturbance passed over the North Pacific, shifting radio signals and sparking brief communication outages at sea. Individually, these are minor events. Together they sketch a pattern we're only beginning to understand. A web of interaction between light and rock, particle and plate, space and soil. It's worth noting that auroras, for all their beauty, also generate currents, called geomagnetically induced currents, or GICs, that can flow through the ground. These currents have been known to interfere with power grids, especially in areas with high conductivity in the crust. In rare cases, they've affected pipelines, causing unexpected corrosion. And where electric fields meet sensitive tectonic zones, there is some speculation that these same currents could influence fault behavior, if not to cause a quake, then perhaps to shift the clock just slightly. Astrophysicists still debate the strength of this connection. Most agree that auroras themselves are not a threat, but the conditions that create them, those shifts in space weather, those subtle pushes and pulls, are worth listening to. Atlas reminds us of this, not by sending a message, but by passing through the medium that carries them. Its journey is quiet, but the space around it is not. Magnetic fields bend. Solar particles scatter. The sun perhaps feels the ripple, and when the sun changes its rhythm, Earth listens, not with panic, but with subtle movement, a flicker in the sky, a drift in pressure, a murmur underground. Tonight, if you live far enough north or south, you might see those lights. You might look up and watch the sky shimmer in silence. You might feel, somewhere in your chest, the strange recognition that you are part of something vast, something still unfolding, and below the earth hums, not loudly, not urgently, but softly, like a memory. Far above, the auroras dance in silence, but beneath our feet, an older rhythm persists, one shaped not by light, but by gravity. The moon, ever present in the night sky, pulls at our oceans with a patience that has lasted billions of years. We feel its influence most visibly in the tides, where water rises and falls with a grace that mirrors the moon's path. But water is not the only thing the moon moves. Beneath the surface, in rock and molten metal, it stirs something deeper. These are Earth's solid tides, imperceptible shifts in the crust caused by lunar gravity. The ground lifts and falls by centimeters, sometimes more, depending on location and depth. Over time, this constant flexing wears on faults. It doesn't cause earthquakes directly, but it may bring a fault closer to release, especially one already under strain. Now consider the sun. Its gravity, though much farther away, is stronger than the moon's. It too contributes to these tidal forces, pulling the Earth in a slow, stately dance. When solar and lunar tides align, their effects amplify, creating moments of heightened stress across Earth's crust. These alignments are predictable, but their outcomes are not, and lately something curious is happening. The timing of recent quake swarms and deep tremors appears to coincide more often with these tidal peaks. It's subtle, and it doesn't always hold. But in regions like Southeast Asia, the Western Pacific, and the Southern Andes, researchers have noticed that seismic activity sometimes clusters around the times when both sun and moon are aligned in their pull. Could it be that the combined gravity of these bodies, magnified perhaps by disturbances in the sun's own behaviour, is nudging Earth's deep interior toward motion? Into this delicate balance comes 3I Atlas, not massive in itself, but arriving at a moment of resonance. As it passes through regions of gravitational complexity, such as the orbital pathways of Jupiter and Saturn, it disturbs the deep gravitational currents of the solar system. Even slight changes here may ripple outward, subtly altering the gravitational profile of the inner planets. Though we cannot feel it directly, Earth may respond in quiet ways. The molten outer core, sensitive to tidal forces, may shift in its flow. The boundary between core and mantle, already a zone of intense energy, might become more unstable. These changes don't announce themselves, they build slowly, like the tension in a stretched bowstring. Lunar tides have long been linked to volcanic activity. In places like Hawaii, Iceland and Indonesia, eruptions have been observed to occur more frequently during peak tidal stress. This doesn't mean the moon causes the eruptions, but it may contribute to their timing, like a conductor raising the baton just before the music begins. Now, with solar activity increasing, and the influence of 3I Atlas possibly nudging that activity further, we find ourselves in a moment where gravitational rhythms, lunar, solar and interstellar, overlap. A kind of cosmic chord, played not with sound, but with force. Astrophysicists still debate whether such alignments produce measurable effects. Some argue the gravitational forces involved are too small to matter. Others point out that resonance isn't about strength, it's about timing. A system already vibrating at the edge of change may respond dramatically to the smallest of nudges. This idea is supported by observations from Earth's deep interior. seismic sensors placed miles underground have detected low-frequency tremors known as non-volcanic tremor. These are not caused by surface events, but by the movement of rock along deep faults. They often occur in clusters, and they often line up with lunar-solar gravitational peaks. Even more intriguing, these tremors have been detected in places not prone to surface quakes, suggesting that deep Earth may be more dynamic than we once believed. It listens to the tides, it moves in response, and perhaps it also listens to the sky. Instruments like GRACE, short for Gravity Recovery and Climate Experiment, have measured changes in Earth's gravity field over time. Some of these changes are seasonal, tied to water movement. Others appear to align with shifts in mass distribution deep within the planet. The data is complex, but it tells us that Earth's gravity, like its crust, is not constant. It breathes, it adapts, it feels. Perhaps then, it also feels the presence of something like 3I Atlas, not directly, but through the chain of influence. A shift in solar gravity, a change in the sun's tidal pull, a quiet signal received by a molten sea hidden beneath our feet. And if the moon and sun can raise tides in solid rock, what else might be stirred by their changing alignment? Tonight, we drift on a planet shaped by forces we cannot see. Lunar light on the water, solar gravity in the core, a passing traveller altering the rhythm just slightly, and deep beneath the surface, a slow, ancient memory wakes, like something that once moved, now remembering how. So we settle here, between sky and stone, listening not for answers, but for echoes, not for alarms, but for patterns. The moon pulls, the sun follows, and far beyond them both something new enters the dance. Far from the familiar paths of planets and moons, there are regions of balance, quiet points in space where gravity from multiple bodies cancels out, creating stillness amid motion. These are called Lagrange points, and though they are invisible, they are profoundly important. Like eddies in a stream, they allow objects to linger in the flow of orbital currents without drifting away. Tonight, as we follow 3I Atlas on its journey, we find ourselves nearing one such crossroads. There are 5 Lagrange points in each two-body system, such as Earth and the Sun. Of these, L1 and L2 are often home to spacecraft, like the Solar and Heliospheric Observatory or the James Webb Space Telescope. L4 and L5, positioned ahead and behind Earth's orbit, are more stable. Objects that reach them can remain there for centuries, slowly circling a region of calm. It's here, in these gravitational pockets, that something curious may be happening. As 3I Atlas continues its approach toward the inner solar system, its trajectory may take it near one or more of these zones, not directly into them, but close enough to influence or be influenced by the delicate gravitational balance they hold. These points are not empty. Some are home to clusters of dust or small asteroids, and they are sensitive. A small disturbance in their environment, be it from solar wind, magnetic pressure, or the gravitational pull of a passing object, can ripple outward through the orbital system. Though 3 Atlas is not massive, its passage through this complex region of gravitational tension could create minor shifts in balance. And those shifts, in turn, might alter the timing or structure of solar plasma streams flowing past Earth. Imagine a river, and imagine a stone dropped far upstream, not a large one, but placed just right. The ripples it makes are subtle, but they travel. By the time they reach a bend in the river where eddies swirl, they might change the flow just enough to alter everything that follows. Some researchers believe that interactions near Lagrange points can affect how solar wind is shaped and channeled. These changes might influence the amount of energy Earth receives, not in ways that alter our climate immediately, but in smaller rhythmic fluctuations that impact the magnetosphere, the ionosphere, and even the deep crust. Lagrange points are also zones of slow resonance. Because objects can linger there, disturbances in these regions can persist longer than they would elsewhere. If 3 Atlas passes close to such a point and nudges it even slightly out of equilibrium, that imbalance could echo through solar plasma for days or weeks. Astrophysicists still debate how strong such effects might be. In conventional models, only massive bodies significantly affect gravitational dynamics. But in more refined simulations, ones that factor in plasma flow, electromagnetic interactions, and system-wide resonance, the influence of small perturbations is less predictable. What matters most is timing and geometry. We now know that certain solar phenomena, such as co-rotating interaction regions, where fast and slow solar winds collide, are shaped by the structure of interplanetary space. These regions can become compressed, forming boundaries that carry more energy toward Earth. A disturbance near a Lagrange point might shift such a boundary, changing how and when that energy arrives. If Earth receives a pulse of solar wind earlier or later than expected, its magnetic field may respond differently. Some pulses strengthen the field temporarily, others create geomagnetic storms, and in some cases these disturbances coincide with tectonic events, again, not necessarily as causes, but perhaps as contributors to a system already on the edge. To explore these interactions, missions like the Deep Space Climate Observatory, DSCOVR, and the upcoming ESA Vigil spacecraft monitor solar wind near Lagrange points. They send data back in real time, allowing scientists to track how the sun's breath changes moment by moment. These observatories are not looking for objects like 3I Atlas, but perhaps, unintentionally, they are already seeing its effects. On Earth, the response to these shifts may be subtle, a brief fluctuation in the magnetosphere, a momentary drop in radio signal strength, a rise in atmospheric density at the edge of space, or, deep below, a soft rearrangement of stress along a fault line, invisible to the eye but detectable to the patient listener. We are that listener now. We lie beneath a world whose surface hides a restless interior, and that interior listens not just to the pull of the moon or the warmth of the sun, but to the fine structure of space itself, to the places where gravity balances, where light slows, where the patterns of movement form their own kind of stillness. Lagrange points are part of this stillness. They are the quiet stations between planets, and they are part of the stage on which 3I Atlas now moves, so we imagine it passing, a dim object barely reflecting sunlight, unnoticed by most. But in its silence it stirs something, not with force, but with presence, like a thought passing through a dream, like a ripple moving through a still pond, and in that ripple something shifts. Perhaps nothing happens, or perhaps far away and deep below, a plate moves, a fracture lengthens, a whisper grows louder, and we, watching sky and earth alike, keep listening. As we drift farther from the warm inner solar system, the light grows dimmer, but the mysteries deepen. Out past Mars, Jupiter, and Saturn, where the sun is only a pale disk in the sky, moons drift in cold orbits, wrapped in ice and shadow. Some of these moons are silent. Others, though, breathe slowly through fractures in their frozen crusts. These are the cryovolcanoes, the ice volcanoes, and they tell us that even in deep cold, worlds can tremble. On Enceladus, a small moon of Saturn, geysers of water and ice plume hundreds of kilometers into space from cracks near its south pole. These jets originate in a hidden ocean beneath the crust, kept warm not by sunlight but by tidal flexing. Saturn's immense gravity pulls and squeezes the moon as it orbits, generating enough internal friction to melt ice deep below. This process, tidal heating, acts like a heartbeat for Enceladus, sending rhythmic pulses through its icy shell. Europa, one of Jupiter's moons, shows similar signs. Its surface is laced with long, crisscrossing fractures, like scars across ancient ice. Beneath it lies a vast, subsurface ocean, more voluminous than all of Earth's seas combined. Occasionally, faint plumes rise from Europa's surface as well, hinting at venting processes deep below. What's striking is that these moons, despite their distance and silence, exhibit seismic behaviour, not quakes in the traditional sense, but tidal shaking, ice cracking, oceans sloshing, subsurface chambers collapsing and refreezing, all of it driven by external gravitational forces, by the motion of these moons through fields of pull and pressure. And here on Earth, the echoes of such dynamics are not unfamiliar. We too are pulled and pressed by the gravity of larger bodies. The Moon, the Sun, and perhaps faintly, objects like 3I Atlas. While we do not have a global ice shell or a subsurface ocean, we have a molten mantle. We have fault lines held tight under stress, we have pressure building beneath our feet, and perhaps, like Europa or Enceladus, we are more responsive to gravitational rhythm than we know. Recent observations of cryovolcanoes have changed how we think about seismicity. For years, scientists believed that these icy bodies were geologically dead, but now we know they breathe, they shift, they erupt, and all of this happens not in response to internal heat alone, but to alignment, to orbital dynamics, to timing. Could it be that Earth too has subtle cryovolcanic analogues? Places where pressure from beneath builds and releases, not through fiery eruptions, but through fluid migration, slow deformation, and silent rupture. Some researchers studying deep Earth fluid movement have begun using the term fluid-triggered seismicity. This refers to small quakes caused not by tectonic slip alone, but by the migration of pressurized fluids through fault zones. These fluids, often superheated brines or carbon-rich gases, can reduce friction and tip a fault toward movement. And here, the link to cryovolcanoes becomes more than metaphor. For on Enceladus, the plumes begin with subsurface pressure. On Earth, so do many quakes. In both cases, timing matters. A tidal pulse, a gravitational alignment, a shift in stress. Each can serve as a trigger. What makes this relevant to 3 Atlas is not its size or speed, but its participation in the greater gravitational network of the solar system. As it moves near large bodies like Jupiter, it may subtly alter their orbital motion. These shifts, though tiny, can change tidal timing across the system. The Sun may alter its own outflows in response, and those outflows may, in turn, modulate how Earth is pulled and pressed, both on the surface and below. Astrophysicists still debate the reach of these effects. But there is growing interest in the resonance between distant events and local seismicity. The movement of cryovolcanoes in the outer solar system offers a kind of parallel, proof that even small periodic forces can produce motion where once there was only stillness. It reminds us that quiet does not mean inactive. Instruments aboard the Cassini spacecraft allowed us to witness the eruptions on Enceladus in real time. Future missions to Europa will do the same, diving through the Moon's atmosphere to sample plumes and measure seismic activity from orbit. We are listening, even in the farthest places, and as we listen outward, we listen inward too. Deep within our own planet, pressure builds, not just from the grinding of plates, but from the long, slow rhythms of fluid, heat, and gravity. Perhaps Earth's mantle is not so different from Enceladus's ocean, layered, moving, held in tension. It's easy to think of Earth as isolated, but in cosmic terms we are linked, by gravity, by resonance, by shared rhythm. So tonight, we imagine cryovolcanoes whispering through the dark, silent fountains of ancient water rising in slow motion through space. We imagine their timing governed by tides we cannot see, and we wonder if, beneath our own crust, something similar stirs. Perhaps Earth listens not just to the Moon and Sun, but to deeper alignments. Perhaps the arrival of 3 Atlas changes that music slightly, adds a note to a distant chord. Perhaps that note reaches all the way to Enceladus, and all the way back to us. Not far from the orbit of Earth, in the quiet ochre of the Martian sky, a different kind of tremor has begun to whisper. On a planet long thought dead, dry and geologically silent, subtle movements stir beneath the dust. Thanks to a lone instrument placed gently on its surface, we now know that Mars too has a pulse. The InSight lander, a robotic geophysicist sent to Mars in 2018, carried with it a tool called SEES, the Seismic Experiment for Interior Structure. Nestled beneath a windshielding dome, this seismometer has been listening carefully to the red planet's silence. What it hears are Mars quakes, small, ghostly tremors that roll through the crust without warning, often without any known cause. For much of its mission, InSight recorded faint repeating rumbles, many so small that they could only be detected in the stillness of Martian night. But some quakes were stronger, and a few emerged from unexpected depths. Unlike Earth, Mars lacks active plate tectonics. There are no shifting continents, and yet the crust moves. Something inside presses outward. Scientists believe these quakes may be driven by thermal contraction, Mars slowly cooling, shrinking and cracking. But some signals hint at more complex forces. A few tremors came from beneath known fault zones like Cerberus Fossae, where ancient lava flows once surged. Others emerged without explanation, from regions thought geologically dormant. These discoveries have reshaped our understanding of seismic life in the solar system. Mars is not a frozen relic. It breathes slowly, and it listens too. Could it be that the red planet, like Earth, responds to changes in solar behaviour? Could it be that both planets, though vastly different, are moved by the same quiet song? Solar wind does not stop at Earth. It continues outward, bathing Mars in charged particles. Without a global magnetic field to shield it, Mars absorbs more of this energy directly. Its thin atmosphere offers little protection. During solar storms, the surface receives pulses of radiation and electric charge that may penetrate deeper than we once assumed. Mars may not have tectonic plates, but it has faults, and it has magma, frozen in places, perhaps flowing very slowly in others. It is not impossible that energy from above, arriving through solar or cosmic channels, might nudge a fault just enough to cause motion. What makes this compelling is the timing. Some of the more unusual Mars quakes recorded by InSight occurred during or shortly after increased solar activity. Again, the pattern is not consistent enough to draw hard conclusions, but it raises a beautiful possibility that seismicity on Mars is not isolated from the Sun's mood. And so, we widen our lens. We consider Earth not as the only planet responding to the rhythms of the sky, but as one of many. Mars, with its thin skin and long memory, may be telling a parallel story, one of a planet quietly influenced by light, by gravity, and by the drift of particles from far away. 3C Atlas II now enters this story. As it moves through the solar system, its presence may not only affect the Sun, but the structure of the heliospheric current sheet, a spiraling layer of magnetic energy that stretches outward from the Sun like a vast rippling ribbon. This sheet, shaped by the Sun's rotating magnetic field, guides solar wind across the system. Planets pass through its folds like ships navigating a vast invisible sea. When the current sheet bends or shifts, the flow of solar wind changes direction. The effects may be minor, or they may trigger electrical and atmospheric responses across planetary surfaces. It's possible, though not confirmed, that 3I Atlas, by passing through sensitive regions of the solar magnetic field, could alter the current sheet's shape just enough to change how the wind arrives at each planet. For Mars, this could mean a sudden burst of charged particles. For Earth, a minor shift in the magnetosphere. For both, a moment of altered pressure. Again, we speak of possibilities, not predictions. Astrophysicists still debate the extent to which the heliospheric sheet responds to small bodies. But as we gather more data from missions across the solar system, patterns begin to form. And each new visitor, from distant comets to interstellar messengers, adds a layer to our understanding. Mars may be quieter than Earth, but its silence is not absolute. Beneath its ochre plains, something turns, something responds, and perhaps, like us, it feels the presence of a traveller passing near. In the late Martian afternoon, when the sky turns rose and the wind stills, InSight's seismometer presses its ear to the ground. It waits, and sometimes it hears a distant rumble, a pulse from below, unannounced, unforced, but real. Could it be that the same rhythm reaches both planets? Could it be that deep time connects them through the breath of the sun and the soft pull of distant bodies? We cannot say for certain, but the thought is not without grace. Two worlds, orbiting the same star touched by the same solar wind, one covered in oceans, the other in dust, both listening. And somewhere beyond them both, a silent object moves through the dark, altering things in ways we do not yet see. In the vast catalogue of stellar oddities, there exists a kind of star so intense, so magnetic, that its very presence bends the fabric of nearby space. These are magnetars, neutron stars born from the collapsed cores of massive suns, compressed into a sphere just a few kilometres wide, yet spinning with unimaginable energy. Their magnetic fields are the strongest known in the universe, trillions of times more powerful than Earth's, and when they shift or crack, they send out pulses that ripple across the cosmos. Unlike black holes, magnetars do not vanish from view. They remain visible, sometimes quietly, sometimes bursting with brief, powerful flashes of X-rays and gamma rays. These flares are so energetic that, on rare occasions, they can be detected even from galaxies far beyond our own. And yet, despite their distance, they remind us of something close, that even compact bodies, though small in size, can shape the environment around them in ways that reach far and wide. What connects a magnetar to our current drift through solar tremors and interstellar guests? It begins with timing. Just as Earth's seismic mood has subtly shifted, and just as 3i Atlas draws nearer to our Sun, magnetar activity has also seen a quiet rise. Over the last 2 years, a number of magnetars have emitted soft gamma repeaters, brief, intense flashes of energy. Most are harmless to us, too distant to do more than cause a blip on our sensors. But they represent a form of cosmic motion, a distant heartbeat. Some astrophysicists have speculated that magnetar bursts, particularly if they interact with interstellar plasma, could create wavefronts of electromagnetic disturbance. These wavefronts, travelling at near the speed of light, ripple through the cosmic web, subtly shifting particle densities in their path. Now imagine through Atlas, a small but fast-moving body crossing through such a wave. It doesn't cause the disturbance, but it feels it, and perhaps just slightly redirects its flow. The redirected stream in turn bends a tendril of solar wind, and from there the chain continues. The sun responds. Earth's magnetosphere shifts, and somewhere below our feet, a fault line feels the slightest change in pressure. Is this too poetic? Perhaps. Astrophysicists still debate whether magnetar bursts have any influence on our local space weather. The distances are vast and the attenuation of energy is severe. Yet our instruments sometimes record unexplained fluctuations in cosmic rays or geomagnetic background during these bursts. Weak signals, but persistent. The resonance between these events, however faint, invites a broader view. What if our solar system is more embedded in the cosmic web than we think? Not isolated in a bubble, but part of a much larger field of interaction, a space where magnetars, solar cycles, planetary tremors, and interstellar objects form a tapestry of slow influence. Earth, in this view, is not a closed system. It is a node, a listening point in a vast ancient network. One curious detail: in early 2025, as 3i Atlas began nearing Mars, a magnetar in the constellation Vulpecula emitted a brief but unusually strong burst. Instruments on Earth and in orbit recorded it clearly. Just 2 days later, a swarm of deep, low-frequency earthquakes occurred in the western Pacific, beneath the sea, in a region not known for such clustered activity. Coincidence? Likely. But then again, there was no solar flare, no obvious local trigger. Some researchers are beginning to look at these chains of timing, not to assert causation, but to open new windows. If Earth responds to cosmic rays, if magnetars alter interstellar particle fields, and if 3I Atlas is passing through those fields while simultaneously coinciding with a solar upswing, then we are watching a moment of rare intersection. And perhaps this is the heart of the matter. Not that any one object causes a quake, or a flare, or a pulse of movement, but that all these events exist within the same interconnected space. A space where motion begets motion, where a flicker in one corner sends ripples outward, and a silent body like 3I Atlas becomes part of that motion, gently shifting the flow of consequence. Magnetars, distant as they are, remind us that extreme forces can arise from small spaces. That intense influence is not always loud. Sometimes it moves beneath perception, until the system it touches begins to change. Perhaps Earth's molten core, buried beneath layers of stone, feels such ripples more readily than we do. Perhaps the magnetosphere, always dancing with the sun's light, adjusts without us noticing. And perhaps, like a tuning fork responding to a distant bell, our planet sometimes hums in sympathy with forces it cannot see. So we lie here, between the breath of a magnetar and the path of an interstellar visitor. We feel the faint pull of the moon, the warmth of the sun, and now, perhaps, the whisper of something more distant, something that doesn't need to arrive in force to matter. It only needs to be here. Every moment, whether we feel it or not, countless particles pass through our bodies, our homes, our cities, and our Earth itself. They come not from the sun, but from the relics of stars long gone. These are neutrinos, tiny, nearly massless particles that stream across the cosmos at close to the speed of light, silent messengers from the deepest reaches of time. And tonight, as we drift deeper into this quiet tapestry of influence, we follow the path of these ancient travellers. Neutrinos are born in the hearts of stars during nuclear fusion. They are also released in supernovae, in the collisions of neutron stars, and in the slow decay of radioactive elements. Most of them, though, come from the sun. Every second, trillions pass through your hand, through your pillow, through the Earth itself. Almost none interact with matter. They are like whispers that never meet an ear. But a few do interact. A few leave tiny traces, flashes of a light in tanks of ultra-pure water deep underground, or in the frozen ice of detectors like IceCube at the South Pole. From these rare interactions, we learn about their origin, their energy, and the stories they carry. What's curious is this. In recent years, a slight change has been noted in the neutrino background. It is subtle, barely outside the margin of error, but persistent. Some detectors have observed fluctuations in neutrino arrival rates that do not correlate directly with solar output. Where are these extra neutrinos coming from? Could they be echoing from a recent supernova, their wavefront only now reaching us? Or are they passing through us from sources we've yet to detect? And could objects like 3I Atlas, as they pass through the interplanetary medium, affect the way these neutrinos arrive? It's unlikely that such a small object could block or reflect neutrinos in any significant way. They pass through entire planets without slowing. But what's more interesting is whether 3I Atlas is itself moving through a region of space with altered neutrino density, a place where the past still echoes, just faintly. If so, it may be helping to carry or redirect streams of particles left behind by old cosmic events. And when those particles reach Earth, they may not cause anything dramatic, but they may contribute to a kind of pressure. Not physical pressure in the traditional sense, but energetic influence felt not in bulk but in balance. Some researchers now study what's called neutrino tomography, a way of imaging the interior of planets by observing how neutrinos pass through them. Earth's core in this way becomes not just a mystery but a lens, a place that might resonate differently depending on the type and density of particles flowing through it. Imagine Earth's core as a great slow drum. Neutrinos, in theory, tap against it constantly. Most pass through, but under just the right conditions their presence might cause a faint vibration. Combine this with other subtle influences, solar wind, magnetic fluctuation, tidal stress, and the system begins to feel more like a musical instrument than a machine. Astrophysicists still debate whether a neutrino flux can meaningfully influence seismic behaviour. Most models say no, but a few suggest that in ultra-sensitive systems, deep magma chambers near critical pressure for instance, cumulative influences might matter more than we think. And then there is the philosophical possibility that Earth's behaviour, from tremors to tides, reflects not just local forces, but a woven response to all of space-time's slow vibration. That our planet, in some deeply physical yet poetic way, is an ear pressed against the cosmic wall. In this light, 3 Atlas becomes more than a rock. It is a traveller moving through currents we barely understand. Neutrino winds, dark matter clumps, gravitational fields left behind by passing stars. As it sails toward the sun, it carries the memory of space long crossed. It doesn't shine, it doesn't roar, but its motion is real, and perhaps the silence it brings is full of signals we've only just begun to hear. When neutrinos from distant galaxies pass through Earth, they do so with no regard for our day or night. They arrive constantly, like ancient starlight, unbent by magnetic fields, untouched by gravity's curve. In a way, they are the purest time travellers, uninterrupted, unhurried. And if they do influence us, it would be not with violence, but with grace. A faint thickening of energy, a gentle shift in balance, a reminder that we're not alone in this web of influence, that we're always being touched by events far away. 3 Atlas is now deep within the heliosphere. It crosses particle flows, magnetic ripples, and yes, perhaps regions of enhanced neutrino density. As it does, it becomes part of the story, an object that both receives and redirects. A stone dropped into a pool, not for the splash, but for the ripples it joins. On Earth, seismometers continue their slow listening. Detectors beneath mountains track the passage of neutrinos with patient quiet. Astronomers watch the sun for subtle flares, and solar physicists monitor the twisting sheet of magnetic current flowing through space. All are parts of the same observation, and here we are, small, wandering beings, listening for a song made of particles, gravity and motion. A song so soft it passes through stone, through silence, through time itself. The sun is not silent. Even in its stillest moments, it hums with layers of motion, slow, internal oscillations, roiling plasma on its surface, and bursts of magnetic tension that sometimes snap into the void. To us, from Earth, the sun appears steady, like a constant flame in the sky. But beneath that bright surface there is rhythm, there is music, and some scientists now wonder whether, in a strange and subtle way, the sun is listening. The idea may seem poetic, but it emerges from real observations. Within solar physics, researchers have long studied oscillations known as helioseismic waves, sound waves trapped inside the sun, bouncing through its hot, dense interior. These waves help scientists map the sun's inner structure, just as seismologists use earthquakes to study Earth's mantle and core. The sun vibrates with countless overlapping tones, creating a symphony of frequencies that change as its magnetic field evolves. These waves are not audible to us, of course, but they can be measured, and lately some have been shifting. Small changes in the frequency and amplitude of solar oscillations have coincided with unexpected solar flares and magnetic disturbances. These aren't part of the usual 11-year cycle. They arrive out of rhythm, as though something subtle is influencing the tempo. Could the presence of an interstellar object like 3I Atlas passing through the heliosphere change how the sun vibrates? Directly, this seems unlikely. The sun is massive, millions of times more massive than 3I Atlas. But in a system governed by resonance, direct force isn't always the key. Sometimes timing is. If 3I Atlas moves through a region of altered plasma density, perhaps a relic of past solar activity, or an interstellar filament, it could, in theory, redirect or delay a solar wind stream. That stream, altered in speed or trajectory, might fold back toward the sun and interact with its outer magnetic field, and in doing so, it could change the surface dynamics just slightly, adding or subtracting energy from specific regions, nudging oscillations off their expected course. This is speculative. Astrophysicists still debate the scale at which such feedback loops could occur, but some models of solar behavior now include external magnetic inputs, not just from planetary alignments, but from interactions at the edge of the heliosphere. The sun, it turns out, may be more permeable to outside influence than once thought. There's another layer to this as well, solar acoustic waves. These are pressure waves, like ripples spreading through the sun's interior. They rise and fall based on surface conditions, and they sometimes exhibit strange asymmetries. In the last few years, certain solar active regions have shown unexpected acoustic signatures, hints that energy is being delivered or dissipated in irregular ways. Some solar physicists have wondered whether these signatures represent the sun responding to external magneto-hydrodynamic pressure, not in large swings, but in subtle shifts, a slight change in incoming solar wind. A bend in the interplanetary magnetic field, a disturbance in particle balance, each might nudge a particular region into instability. Now imagine that 3I Atlas is passing through one of these key regions, a location in the heliosphere where the magnetic field is already finely balanced. Its motion doesn't need to be violent, it just needs to arrive at the right moment, in the right place. Like a finger gently touching the edge of a drumhead, it might not strike, but it could change the tone. And the sun, in its way, may respond. Perhaps with a slightly altered flare, perhaps with a coronal loop that twists just a little tighter, or perhaps with a fluctuation in the timing of acoustic waves, something that will be noticed only months later in the gentle curve of a data plot, rising unexpectedly toward a new peak. If such a response occurs, it may travel back outward. The solar wind carries information not just from the sun, but about the sun. Changes in its density and velocity affect everything in its path, including Earth's magnetosphere, which listens closely to every beat. On our planet, that beat becomes more than data. It becomes action, a geomagnetic storm, a shift in the ionosphere, a flicker in auroras. And sometimes, just sometimes, a subtle change in pressure within the crust, a movement of fault lines already near the edge of motion. There is still no certainty in this chain. Each link is delicate, each influence partial, but the possibility remains a system of resonance from interstellar object to solar vibration to terrestrial motion, a system in which the sun is not only a source, but a receiver, a participant in the wider music of space. This brings us back to 3I Atlas, not massive, not brilliant, but timely. Its motion intersects with regions we're only beginning to map. It glides through currents we barely understand. And its presence, while quiet, may be felt in the way a resonance is felt, not as impact, but as shift. If this is true, it challenges how we think about influence in the cosmos. We often imagine large forces dominating small ones. But in the language of harmony, timing matters more than size. A violin string touched lightly at the right moment can alter an entire chord. The sun, too, may be listening. Not in consciousness, but in structure, in energy, in rhythm, and Earth in turn may respond. So tonight, as we lie beneath a sky that seems still but is not, we listen for that rhythm. We feel the warmth of the sun, carried to us across millions of kilometres, and we wonder whether somewhere in that warmth a new note has been added, a quiet tone, a soft pulse. Perhaps it began with 3 Atlas, or perhaps it began long ago, and we are only now able to hear it. All around our planet, even in the absence of lightning or storm, the Earth hums with electromagnetic energy. Not the kind that powers our homes or lights our cities, but something older, deeper, and more rhythmic. These are the Schumann resonances, a set of low-frequency electromagnetic waves that reverberate between Earth's surface and the lower edge of the ionosphere. Like the quiet breath of the planet, they pulse endlessly, shaping the background rhythm of life itself. First predicted in the 1950s, Schumann resonances are now measurable with precise instruments. They occur primarily at frequencies around 7.8, 14.3, and 20.8 Hz, corresponding to natural harmonics in the Earth ionosphere cavity. They're generated largely by global lightning activity, but their persistence, even in calm weather, speaks to a more stable resonance, a kind of planetary heartbeat. What makes these resonances fascinating in our journey through cosmic tremors is their sensitivity. They are easily influenced by changes in the ionosphere, which in turn responds directly to space weather, solar flares, geomagnetic storms, and fluctuations in charged particle density. When the sun sends a surge of energy toward Earth, even if it doesn't spark auroras or disrupt communications, it can still alter the boundary conditions that define these frequencies. Lately, researchers have observed unusual shifts in the amplitude and clarity of the Schumann bands. These changes often follow solar events, but sometimes they seem to precede them. It's as if Earth itself is anticipating a shift, or perhaps more likely it's already feeling subtle electromagnetic changes travelling faster than the solar wind. And now, with 3I Atlas moving through the inner solar system, we wonder if its presence might be adding to this quiet stir. It doesn't generate these resonances, of course, but it could influence the shape of the solar wind that arrives at Earth. If 3I Atlas disrupts or refracts the flow of plasma in even a small way, the altered stream could modulate how the ionosphere conducts or reflects radio waves. This is important because the Schumann resonances are not just passive background tones. They interact with biological systems. Studies have found that the human brain's alpha waves, which govern states of calm and rest, overlap closely with the fundamental Schumann frequency of 7.8 Hz. Some researchers have suggested that our own sleep cycles, moods, and cognitive patterns might subtly sync with this planetary hum. It's speculative, yes, but not impossible. We live within this resonance field day and night. And if that field is affected by solar shifts, if it rises or dips in response to changing solar wind shaped by passing interstellar bodies, then it's possible we feel those shifts in ways that science is only beginning to explore. Even more curious is the potential connection between Schumann resonance anomalies and seismic activity. In some cases, shifts in resonance have been observed days before major earthquakes. The mechanisms remain unclear. One hypothesis is that as stress builds within the Earth, changes in crustal conductivity subtly alter the planet's electromagnetic environment, creating feedback between Earth and ionosphere. In this sense, an earthquake is not only a rupture in stone, but in signal. If 3I Atlas contributes even gently to a chain of solar and geomagnetic effects, if its motion perturbs the heliospheric current sheet or the flow of solar particles, then the resulting cascade may touch the ionosphere, and from there, perhaps, ripple into the resonance chamber of Earth itself. This would not be a direct cause and effect, but rather a kind of orchestral interplay, pressure and tone, field and feedback, Earth's crust, Earth's sky, and the charged space between them forming a single vibrating system. Recent experiments with extremely low frequency ELF monitoring have detected quiet anomalies during solar disturbances changes in the waveform of Earth's natural resonances, sometimes coinciding with ground tremors. Again, these signals are faint. They require sensitive equipment and careful filtering, but the pattern, however elusive, continues to whisper. Could it be that the very rhythm of our planet is shaped not only by internal forces, but by a wider cosmic dialogue? That the resonance we feel, often too low to hear, carries information from solar moods, from magnetic shifts, and from the drift of bodies like 3i Atlas. Instruments across the world continue to listen. From deep in Siberian forests to quiet valleys in Japan, researchers monitor the Schumann bands as though listening for a change in breath. And sometimes they find it. A slight quickening, a fading tone, a new harmonic emerging and then slipping away. It may be nothing, or it may be everything. For just as we look outward for signs of change, in comet paths, in flares, in planetary quakes, so too we must look inward, to the signals Earth gives us through its own electromagnetic voice. And so we drift tonight through this layer of the unseen, a realm of invisible frequency, wrapping the world in quiet song. A realm that responds to light we cannot see, to particles we cannot feel, and to travellers whose paths cross ours without fanfare. Perhaps even now, as through Atlas bends the edge of the sun's magnetic sheet and reshapes a solar windstream, the Earth's hum has already changed. Perhaps our heartbeat, our shared field of resonance, has shifted slightly to match. We may not hear it, but somewhere, our planet does. As we coast deeper into this quiet river of influence, we begin to sense the turning of a larger wheel, the unfolding of a new solar mood. The sun, after years of relative calm, is beginning to stir with a kind of subtle urgency. Not explosive, not frantic, but noticeably more alive. A few years ago, forecasters predicted that solar cycle 25 would be weaker than the one before, but now the data is shifting. Sunspot numbers are exceeding projections, flares are growing in frequency, the sun is waking, and perhaps reacting. Solar cycles are not just rhythms, they are histories. Each one is recorded in the sun's magnetic field, which flips direction approximately every 11 years. This flipping isn't smooth, it comes with tension, with eruptions, with changes in solar wind speed and magnetic complexity. And these changes don't just stay near the sun, they spread outward across the entire heliosphere, touching every planet in their path. Earth, bathed in this stream, feels the change. The magnetosphere becomes more active. The ionosphere thickens and thins in complex patterns. High-altitude radiation levels fluctuate, and, as we've been exploring, the crust itself may respond, subtly, delicately, but measurably. Now, consider this. 3i Atlas has entered our system just as the sun's activity begins to rise earlier and stronger than predicted. Is this a coincidence of timing, or is it part of a feedback loop we don't yet understand? It may be tempting to dismiss this alignment as poetic rather than physical, and yet astrophysicists are beginning to re-express the sun not just as an engine, but as a resonator, responsive to the environment it moves through. The solar system is not empty space. It is a sea of plasma, gravity, relic radiation, and charged dust. As objects pass through this sea, they disturb it, and the sun, enormous though it is, swims through that same current. Recent studies of solar wind structure show that even small changes in the density of the interstellar medium, regions of higher or lower particle concentration, can affect the speed, angle, and shape of solar outflows. And as those outflows change, so too does the solar magnetic field that wraps around the entire system. The idea here is not that 3i Atlas is causing the sun to flare, but that it may be participating in a broader set of interactions, tipping balances, nudging flows, adding one more thread to a tightly woven web, and the sun, in its awakening, sends those threads back outward, toward Earth, toward Mars, toward the cold outer regions where spacecraft now monitor the frontier of space weather. One piece of evidence worth noting: the recent clustering of mid-level solar flares on the Sun's far side. These flares occurred in regions that rotated into view just days after 3 Atlas passed through a particular segment of the heliosphere, regions that had been dormant for much of the previous year. When those regions rotated into view, their magnetic complexity had increased. New sunspots had formed. Active regions began to pulse. Again, we cannot say this was caused by the passing of an object. But the alignment of timing invites curiosity. Was the Sun responding not to mass, but to pattern? To a change in the interplanetary current system? To a shift in plasma density at the solar boundary? This brings us to a deeper truth. The Sun is not just our star. It is a participant in the structure of the galaxy. It moves along the Milky Way's spiral arm, travelling through regions of differing magnetic composition and cosmic dust. Its behaviour, while cyclic, is also reactive, shaped by long journeys through the galaxy's grand geometry. And now, with 3 Atlas entering the inner system, the Sun is adjusting once again, flaring slightly brighter, shifting its wind, twisting its magnetic field in subtle new shapes. Whether this is coincidence or choreography, we do not yet know, but we are here to witness it. On Earth, solar mood affects more than machines. Some researchers have explored correlations between solar cycles and biological patterns, plant growth, migration, even human mood and behaviour. The results are mixed, often controversial, but the question persists. If solar rhythm affects the field around us, might it also affect what lives within it? We know that geomagnetic storms influence animal navigation. We know that radiation levels during solar maximum can affect cell structures at high altitudes, and we know that some people report changes in sleep or sensitivity during solar storms. Is it too much to suggest that a waking sun might ripple through more than the sky? Perhaps not. Perhaps Earth's systems, from tectonics to temperature, from ocean currents to atmospheric pressure, are tuned to the solar heartbeat more deeply than we understand. And if the Sun is indeed entering a mood of increased activity, early, surprising and strong, then the timing of 3I Atlas becomes all the more intriguing. It may not be the cause, but it may be part of the composition. A visitor from between stars passing through the solar wind, intersecting magnetic lines of force, moving silently through regions of ancient influence. Its presence is brief, but in the context of a resonant system, even brief presence matters. So we watch the Sun rise higher. We listen to its growing hum. We trace the patterns in its light, and we notice what changes beneath our feet as it shifts. A new solar mood has arrived. It is not yet dramatic, but it is clear. The flares are more frequent. The wind is stronger. The auroras dance farther south. The Earth's magnetic field shudders just a little more often, and below, the plates press a little harder. We continue to listen. To the sky, to the Sun, to the Earth. All resonating together, all responding in ways both visible and hidden. And somewhere in the midst of it all, 3I Atlas continues its path. Quiet, dark, and passing. Deep beneath our feet, far below the quiet soils and shifting plates, the Earth holds memories written in stone. These are the silent archives of time, geological records preserved in sediment, crystal, and fault. And like the pages of a book, they contain stories of tremors long past, quakes that shook ancient forests, mountains that lifted slowly from ocean floors, rifts that opened and closed across ages. In this layer of the story, we turn to those hidden records and what they may whisper about cosmic timing. Paleoseismology, the study of prehistoric earthquakes, relies on careful observation of the Earth's scars. In canyons, along fault lines, and deep within drilled cores, researchers examine displaced rock layers, liquefied sands, and uplifted shorelines. These features are dated, sometimes with surprising precision, revealing patterns of seismic activity that span tens of thousands of years. What emerges from this work is not randomness, but rhythm. Earthquakes tend to cluster in time, arriving in waves across centuries. Faults lie dormant, then suddenly leap into motion. In places like California, Japan, Turkey, and Chile, paleoseismic records show repeating cycles every few hundred years, sometimes more, sometimes less. And intriguingly, some of these cycles align loosely with larger astronomical rhythms. One of the most striking examples lies in the Cascadia subduction zone off the northwest coast of North America. There, evidence of massive megathrust earthquakes, similar to the 2011 Tohoku quake in Japan, suggests a recurrence interval of roughly 300 to 600 years. Tree rings, tsunami deposits, and coastal subsidence records all point to a major event occurring in 1700, and before that in sequences spaced by several centuries. Now scientists are asking, could these patterns be influenced by something beyond the fault itself? Could solar cycles, or even deeper cosmic rhythms, play a quiet role in when Earth decides to move? Enter Milankovitch cycles, long-term variations in Earth's orbit and axial tilt. These cycles affect the distribution of solar energy across the planet and are known to influence ice ages. But some researchers propose that they might also impact tectonic stress indirectly through changes in sea level, glacial loading, or even planetary angular momentum. And what if, layered atop those slow cycles, more transient cosmic events also leave their mark? Supernovae, interstellar dust clouds, or the rare passage of objects like 3I Atlas, all could alter solar behaviour, cosmic ray intensity, or geomagnetic stability. The link is not proven, but the idea invites a gentler question. Not whether these events cause earthquakes, but whether they time them. It's a subtle distinction. Earthquakes need internal stress to occur, but they may not release that stress until something nudges the system past a threshold. That nudge might come from a high tide, or a temperature shift, or perhaps from a solar flare, a magnetic wave, or the influence of a passing interstellar body. Recent advancements in ice core analysis and sediment studies have begun revealing hints of correlation between solar activity and geological events. For example, spikes in cosmogenic isotopes, produced by cosmic rays, sometimes align with periods of climatic and geological upheaval. Again, the pattern is weak, but it is there. In Japan, researchers examining buried tsunami layers have proposed a faint connection between tsunami-generating quakes and solar maxima. In the Himalayas, long-term uplift records appear to coincide loosely with glacial and cosmic cycles. None of this proves causation. But the possibility of timing, the idea that Earth's interior might respond not just to internal thresholds, but to external pulses, is gaining quiet traction. Which brings us back to 3I Atlas. Its trajectory cuts across the orbits of the outer planets, moving through regions rich in gravitational complexity. If it passes near a zone where ancient cosmic debris or magnetic turbulence lingers, it could disturb the solar wind in ways that reach Earth weeks or months later. And if Earth, at that moment, is perched on the edge of tectonic release, perhaps along a fault that last moved during a solar maximum centuries ago, the conditions may quietly align. It wouldn't take much. A slight shift in atmospheric pressure, a minor disturbance in electromagnetic balance, a resonance in the Schumann bands, and beneath it all, a fault that's been waiting for millennia might finally respond. We do not need to see this as prophecy or prediction. It is not fate written in the stars. It is instead a deeper form of listening, an acknowledgement that Earth, while self-contained, is not alone. Its crust may crack and fold in response to local forces. But its timing, its rhythm, may be part of something broader, something shared. And in the rocks that hold the memory of past movements, we may begin to see that rhythm unfold. A cluster here, a gap there, a repetition that matches not the calendar but the cosmos. Tonight, As 3i Atlas moves ever closer to the Sun, we imagine the faint possibility that its presence is recorded not in light, but in stone, that somewhere deep beneath the Andes or beneath the seafloor off Alaska or under the silent forests of Indonesia, pressure is building again, quietly, patiently, in tune with something we do not yet fully understand, and we, drifting on the surface of this ancient memory, listen. Far above us, where the darkness between planets folds into interstellar space, gravity weaves its quiet threads. It is easy to think of gravity as a force that pulls, downward, inward, binding objects to orbits and shapes to systems. But gravity also reaches. It touches everything, all the time, even across impossible distances. Tonight, we lean into that thought. We imagine not the violence of gravity, but its patience, not its weight, but its whispers. Every object exerts gravitational force. From the tiniest grain of dust to the largest galaxy cluster, all things tug on all things. The strength of that pull depends on mass and distance, as none, of course. But when systems grow complex, when multiple bodies move together, gravity creates patterns that cannot be fully predicted. Resonances, lensing, tides, spirals, echoes. In the case of 3i Atlas, its mass is negligible compared to planets or stars, but its motion places it into the gravitational flow of the solar system. As it passes near Jupiter's orbit, it may not cause much disturbance, but it may ride existing waves, bend faint paths, and shift timing in delicate ways. Some of the most surprising gravitational effects are not in the direction of motion, but in what they leave behind, perturbations. Like a canoe slipping through calm water, the wake ripples long after the boat has passed. In celestial mechanics, these perturbations can accumulate, altering the trajectories of dust, plasma, or even light itself. Consider gravitational lensing, where massive objects like galaxies bend the light of more distant ones. On smaller scales, similar effects can happen with charged particles and magnetic fields. The paths of solar wind streams, for example, may bend subtly when they pass through changing gravitational gradients, and these bends affect when and how those particles reach Earth. Now, if 3i Atlas passes through a region with multiple overlapping influences, say the gravitational tail of Saturn combined with a dense patch of solar plasma, it might gently deflect those particles, and when those redirected streams finally reach us, they may arrive at a moment that nudges our own planet's systems. This is how influence moves in the cosmos. Not with obvious drama, but through timing and accumulation, through soft changes in angle, through the arrival of a solar wind burst just minutes earlier than expected, through the compression of Earth's magnetotail at a moment of atmospheric sensitivity, through a surge in the ionosphere that causes a pulse in the Schumann resonance, through pressure that reaches the crust in the right place at the right time. Astrophysicists still debate the real-world significance of such cascading effects. The energy transferred may be small, but in highly sensitive systems, like those found in subduction zones, deep faults, or magma chambers, even small shifts can have consequences. A telling analogy lies in the phenomenon of tidal triggering. We already know that the moon's gravity can influence earthquake timing. On land, this is subtle, but under the ocean, in regions like the Mariana Trench, the timing of deep tremors sometimes corresponds to high tides, not because the water causes the quake, but because the system was already balanced on a threshold. If the moon can do this with a small rise in local gravity, might not the arrival of a shifted solar wind, altered by a passing object like 3i Atlas, do the same? One particularly delicate system is the crust-mantle boundary, known as the Mohorovičić discontinuity, or the MOHO. It lies deep beneath us, but it's not uniform. In some places it's jagged, in others smooth. Stress concentrates along these irregularities, and when something tips the energy balance, heat, pressure, fluid, or perhaps electromagnetic charge, a sudden release can occur. Add to this the influence of telluric currents, natural electric currents that flow underground and shift with space weather. These too are influenced by solar wind, geomagnetic storms, and even the tilt of the sun's magnetic field. And these currents, in turn, can change the resistivity of rock layers, altering how stress moves through the crust. What we begin to see is not a single cause, but a convergence. Gravity, plasma, electromagnetic flow, internal heat, all overlapping, all resonating, and into this complex choreography steps a visitor, Theresa's Atlas. It does not strike. It does not orbit, it simply passes through, but in doing so, it participates. We are beginning to understand gravity not just as a pull, but as a presence, as a background song that sets the tempo for all motion. And when a new note enters the melody, the rhythm changes, sometimes in ways we can measure, sometimes in ways we can only feel. Earth's crust is not deaf to these changes. It listens constantly through tension. And sometimes, when the harmonics are just right, it moves. Somewhere tonight, perhaps deep beneath the Himalayas or beneath the Pacific floor, a fault holds its breath. It is close to slipping. The conditions are nearly perfect, and as a minor surge of solar energy, redirected ever so slightly by 3i Atlas, brushes the magnetosphere, a cascade begins. It may not release today, it may not release for weeks, but the conversation has started. So we end this section not with a conclusion, but with a feeling that perhaps the Earth's crust is more attuned to the stars than we ever dared to believe. That perhaps what seems like randomness is instead a long response to a slow and ancient dialogue, a gravity not of force, but of timing. And so we arrive at the edge of the map, where story meets silence, where data gives way to deep time. We've wandered from fault lines to solar flares, from magnetars to Schumann resonances, from icy moons to a single dark traveller, passing quietly through our solar system. All along, one question has shimmered just beneath the surface. Could it be that Earth's tremors, subtle and multiplying, are not just internal movements, but part of a wider cosmic tide? We cannot say for sure. The science is still young, the data still forming, but the patterns, whispers of alignment, timing, resonance, continue to invite us. And somewhere in the long pause between quakes, between pulses of solar wind, we begin to feel something ancient. Earth is not alone. It is woven into the field. We are beginning to understand that influence does not always arrive with force. Sometimes it arrives with a pause, a shadow, a slightly altered flow of particles, a brief delay in the solar wind, a surge in atmospheric charge, and in that moment, barely measurable, a fault that has waited for centuries may find its cue. This is the poetry of thresholds. Systems in balance do not need a push. They need a whisper. It could be tidal stress from the moon. It could be a spike in telluric current. It could be the arrival of a solar flare, its energy subtly redirected by the arc of 3i Atlas through the heliospheric current sheet. Or perhaps it's all of these together. A quiet harmony of causes. We must remember that Earth's crust does not know about 3i Atlas. It does not know about magnetars or current sheets or neutrinos, but it knows energy, it knows stress, and it knows timing. And timing in systems like this is everything. The tremors we've been tracing, the multiplying earthquakes, the swarms, the silent slips, may not be random. They may be answers, not to questions we've asked directly, but to a signal that passed through, so softly we barely noticed. Perhaps it was a shift in the sun's mood, amplified by the passage of a magnetic anomaly. Perhaps it was a buried resonance, echoing from deep within Earth's core, stirred by gravitational waves or by faint neutrino pressure. Perhaps it was the cumulative effect of thousands of small shifts, all culminating now. Perhaps above it all, a visitor passed by, watching nothing, saying nothing, just drifting. And as it crossed unseen magnetic thresholds, it changed the rhythm of the system, like a breeze entering a cathedral and shifting the song. The poetry of Three-Eye Atlas is not in its power but in its timing, in the way it reminds us that motion is everywhere, that what we call space is filled with structure, that even the quietest object can resonate with enormous systems, given the right conditions, and perhaps the Earth knows this. Perhaps, without words, it waits for such moments, not because they tell it when to move, but because they complete the rhythm already unfolding deep below. So we close this chapter not with answers but with reverence, for the fault lines that listen, for the mantle that holds memory, for the magnetosphere that bends and flickers like a veil in wind, for the solar wind itself shaped by a star that sings without pause, and for a silent object born in another star system, now passing through ours, leaving behind no trail but timing, no light but change. We do not need to know everything to feel something real. We do not need to predict to prepare, and we do not need certainty to wonder. Tonight, the Earth rests, the sun pulses. Three-Eye Atlas drifts closer to the heart of light, and we listen. Now let's breathe together, gently, slowly, allowing the hum of the universe to soften in the mind. We've wandered through vast ideas, through stars and stone, through fault lines and flare cycles, and yet the journey has been quiet, no alarm, no rush, only the unfolding of a larger rhythm. Let yourself drift now into stillness, into the silence beneath the data. Imagine the deep ocean crust, unmoving, the slow curl of magnetic lines at the edge of the sun, the long arc of Three-Eye Atlas, quiet as dusk slipping between planets. This is not a world of chaos, it's a world of movement, a slow choreography of gravity and energy, unfolding over eons. Earth's surface, though it shifts, is part of that grace, and you are too. Beneath you, the planet listens. Above you, the solar wind flows. Between them, you rest, safe, small, and perfectly placed. Inhale softly, exhale without force. Let the weight of cosmic time hold you. Even the tremors we spoke of tonight. They pass. They are not threats. They are signals. And you're not alone in receiving them. You're wrapped in starlight, in magnetism, in memory. Let go now. No more questions. Just the lull of slow time. The earth is quiet. The sky is watching. You may sleep.